So welcome you all. So today's topic is historical development of quantum theory. So in this topic we will discuss about the pre-quantum mechanics, classical mechanics, failure of classical mechanics, for example like black body radiations, free development and prior development of quantum mechanics, and what was the later development in the field of quantum mechanics. So coming to the pre-quantum mechanics or classical mechanics. So classical mechanics as formulated by the Sir Isaac Newton in 1642 to during the 1727 and is obeyed by a macroscopic particles such as planets and rigid bodies. However, since the microscopic particles such as electrons, proton, atoms and molecules show wave particle duality, they do not obey the Newton's dynamics or Newton's law. They, however, obey quantum mechanics or wave mechanics, a key feature of which is quantization of energy and angular momentum. So here, actual the theory which was given in classical mechanics is obeyed by the macroscopic, macro means large particles or big particles like big rigid bodies, and not being obeyed by the smaller particles, such as if we discuss about the behavior of electron, protons, atoms and molecule. So here a different theory is required to explain their nature. So this failure of explaining the classical theory is regarded as a need for new theory which is came into light as a quantum mechanics. So here if you see, there are number of example. Once we discuss about classical mechanics, it describes the motion of like baseball, the spinning of a top, it can explain. But once you see the quantum mechanics, it describes the motion of electron and the shapes of molecule, such as even like trans fats and cis fats or molecules, as well as electrical conductivity and superconductivity. So the behavior of this type of property in an element can be explained on the basis of quantum mechanics. If you comes to the failures, there are number of experiment which fails to explain the mechanism of the particular kind of observation. But here atomics and molecular phenomena like molecular spectra is not being explained on the basis of classical mechanics, because the absorption and emission spectra generally gives by the elements at with different energy levels. So the classical physics cannot describe the light particles. For example, if you want to explain the electrons and their behavior and different cells, the electrons is being having the different energy, and on the basis of that different energy, that gives a different type of spectrum like absorption spectrum once it is excited from their ground state to higher state. Therefore a new theory which is able to describe the failure of classical mechanics or classical theory is originated the quantum mechanics, and the failure of the many uh, explanation on the basis of classical mechanics originate to explain that phenomenon with the help of quantum mechanics. We see how the classical mechanics is being failed. So here the much more important example in this is black body radiations. So you all might know what is black body radiations, because a black body is a theoretical object that absorbs all the radiation which is being hit on it. So therefore it reflects no radiation and appears perfectly black, but in general this doesn't happen. So it is also a perfect emitter of radiation at a particular temperature. The black body would emit the maximum amount of energy possible for that temperature. So here if you see, there is number of rules, among which Rayleigh-Jean's law is very important, which try to explain the black body radiations. But here you can see it is an approximation to the spectral radiance of electromagnetic radiation as a function of wavelength from a black body at a given temperature through classical mechanics, or through classical argument. For wavelength, it is P lambda T equal to C kb T upon lambda e power 4. So where P lambda is the spectral radiance, the power emitted per unit emitting area per sterdium per unit wavelength, and C is speed of light, and kb is the well-known Boltzmann constant, and T is temperature in kelvins. So for frequency, the expression is gives as in a form of B nu T equal to 2 nu square kb T upon C square. So here the Rayleigh-Jean's law agrees with experimental results at a larger wavelength or low frequency, if you can see from this graph, so it will be very clear, but strongly disagree at a shorter wavelength or high frequency. So here you can see at x coordinate it is towards the higher wavelength region, and this is the lower wavelength region. So this does not fit at this fit Rayleigh-Jean's law at the higher wavelength region, but does not fits at the lower wavelength region, or you can say at a higher frequency. So this consequences or this kind of behavior is known as ultraviolet catastrophe. So this is inconsistency between the observation and the prediction of classical physics, and this inconsistency is known as ultraviolet catastrophe. It is its resolution is in 1900 with the derivation of Max Planck. So this explanation was explained on the basis of Max Planck's law, which gives the correct radiation at all frequency, was a fundamental aspect of the development of quantum mechanics in early 20th century. So here you can see in 1900 Max Planck empirically obtained an expression for black body radiation expressed in terms of wavelength. So this is given by this expression B lambda T equal to 2hc square lambda 4 into 1 upon hc minus 1 upon E lambda kbt. So these all terms are as usual, like Planck constant, kb, Boltzmann constant. The Planck's law does not suffer from an ultraviolet catastrophe and agrees well with the experimental data. So he explained the concept which was observed in the classical theory was explained on the basis of experimental data by the Max Planck. As the black body radiations cannot be explained on the basis of classical physics or classical theories, which was tried to by the Plancks to explain the classical nature or classical behavior of the radiations. So the classical theory was put forward by the Plancks. So it is called classical theory of radiation or Planck's theory of classic quantum mechanics or quantum theory of radiation of Planck's. So according to this theory, as you know, the energy distributed in black body radiation could not be explained if you try to consider the laws of classical physics. So he has given the uh, different theories or different concepts. On the basis of that, radiant energy is emitted or absorbed discontinuously in a form of teeny bundles of energy known as quanta. If you remember the earlier videos, and the concept of the explanation by the Planck. He explained that the energy is not comes continuously, and it is always being absorbed or emitted in a form of packets or energy packet, which is generally represented as h nu. So each quanta is associated with a definite amount or definite amount of energy, which is equal to h nu. So where E is energy, or you can say in energy in various other units, and nu is the frequency of radiation as usual conventions. So reciprocal S inverse is the reciprocal second, and H is the Planck's constant. So the overall value which is calculated for the H for the Planck's constant was comes 6.626 into 10 raised to the power minus 34 joule second. So here you can see that this explanation is being good for the radiations and good for to explain the quantum nature of the radiation, or the energy is released in a form of quanta, not in a continuous. So the value of quantum energy is also given by hc phi var, or nu, you can say nu var, where nu is the wave number, and you know it is very usual formula, nu equal to 1 upon, or you know this, the wave number is represented by 1 upon, or reciprocal inversely proportional to the lambda. So evidently c nu equal to c upon lambda, and E equal to hc nu. Here a body can emit or absorb energy only in a form of whole number multiple of quantum, rather than a fraction. It always either absorbs or emits the energy in a form of whole number multiple of quantum. So that is quanta is called quanta. So it will be always either 1 h nu, 2 h nu, or 3, or number of h nu or photons. So energy in fraction of a quantum cannot be lost or absorbed. So always whenever either it is emitting or absorbing will be always in a whole number, not in a fraction. So this is known as quantization of energy. So this is called quantization of energy, since it is being either absorbed or emit in case of like absorption spectra or emission spectra, when the photon is comes from their higher energy state to lower energy state, so it release the energy in a form of quanta. So then once it lose the energy, electrons, like it jumps from lower ground state to higher excited state, then it release the form of energy in a form of quanta. So based on this theory, Planck's gives a following expression for energy density, which is being used for to black body radiation. And so the density of black body radiation is expressed like this: EV equal to 8h nu to power 3 upon c cube. So into multiplied by uh, del V upon exponential h nu upon kt, where all terms are as usual at conventional terms like c velocity of light, h Planck's constant, t temperature in Kelvin, etc. So it is adequately accounts for the black body radiation curves at all wavelength obtained at different temperature. Planck was for his excellent works to explain the radiation nature of radiation. So he was awarded a Nobel Prize in 1918 for proposing quantum theory of radiation. So if you see the development of quantum mechanics, the development of quantum mechanics was generally being started in the starting of the 20th century, and Einstein in the same time in 1905 proposed the radiation is itself also quantized according to the same formula, and he used the new theory of to explain the photoelectric effect. So also on the basis of the similar quantum concepts, Einstein also explained the effect of generally observed in case of photoelectric, which is called photoelectric effect. So the following discovery, like at the same century, the starting of the century, Rutherford also gives the concept of nucleus, very famous experiment done by the Rutherford, so to find out the nucleus and give the concept of positive charge on the nucleus in an atom. So Bohr used the quantum theory in 1913 to explain both atomic structure and atomic spectra, showing the connection between the electron energy level and the frequencies of light given off and absorption. So here, the Bohr model, you also know, because there are different orbit or different cells in which the energy is being excited. Once the electron excited from their lower to higher energy state, so at the same time they once lose the energy, then they emit certain quanta. So that quanta is having a different energy with once they are coming with in a different energy levels. So during that they are emitting the light, which is the basis of the emission spectroscopy. And similarly, when it absorbs a certain amount of energy and excited from their ground state to higher state, so that is the basis of absorption spectroscopy. So this is an excellent explanation which was given by the various scientists and to explain the absorption and emission spectra on the basis of classical mechanics. So in the latter, after the Planck and Einstein, in 1924, Louis de Broglie proposed that not only do light waves sometimes exhibit particle-like properties, as in photoelectric effect and atomic spectra, but particle may also exhibit wave-like property. So the de Broglie, he also proposed on the basis of the experimental observation that that light waves sometimes exhibit particle-like property as well, as in case of photoelectric effect and atomic spectra. And this wave-like properties, along with the like in a form of quanta, in a form of energy packets. So he also proposed the wave-like properties of the the photons, which is in comes in a form of packets, but here the particle also having a wave-like properties was de Broglie. So he in 1924 also explained on the basis of the theory of quantum mechanics. So this hypothesis was confirmed by experimentation in 1927 by C.J. Davison and L.H. Gaumer, who observed diffraction of the beam of electron analogous to the diffraction of the beam of light. So this diffraction experiment was done by the Davison and Gaumer. So this makes the basis of like X-ray diffraction spectroscopic techniques, X-ray diffraction. So 2D sine theta, that is the expression is given after this observation. So the two different formulation of quantum mechanics were presented following de Broglie's suggestion. The wave mechanics of at the same time in 1926, Erwin Schrödinger involved the use of mathematical entity, the wave function, which is related to the probability of finding a particles at a given point in space. So the probability of finding an particles, or in case of like a electron or hydrogen like particle atoms, so the equation and mathematical expression was given by Schrodinger. So that is called Schrodinger wave equation. And also at the same time, Heisenberg uncertainty principle was also given on the basis of the quantum mechanics. So the after overall discussion, we discuss about the classical theory, the failure of classical theory with the help of black body radiation, and the experiment done by the Planck's, and his observation shows that black body radiations can be the which is the called ultraviolet catastrophe, which is does not match as per the classical theory, was explained on the basis of quantum mechanics. So the behavior of radiation, like in a form of quanta, or the concept of quantum, is comes after the explanation of given by the Planck's. So the Planck has done the experiment, and that was started after the experiment which he observed to see how does the light is being either absorbed or emitted in a form of quantum. So here few of the references which is being taken over here. Thank you so much. So thank you so much for your patience. Thank you so much.